In this video, we'll be talking about free body diagrams, which we can also call force diagrams. We'll talk about what a free body diagram is, and we'll practice how to create a free body diagram for any object whose motion we may want to investigate. So what is a free body or a force diagram? So what a free body diagram is a diagram, which is just a visual representation, which represents all of the forces acting on an object. So when we talk about a free body diagram, you can think of it like this. We have an object. Let's say, for instance, we're talking about a baseball. And what we're doing when we're creating a free body diagram is it's almost like we're taking a pair of scissors and cutting that object out of reality. So we want to snip, 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 cut the object out of reality and look at just that object. And in creating this reality that we're removing it from, we want to then show all of the forces that were acting on that object when we snipped it out of reality. So in a free body diagram, there are two components. The first is representing the object that we're looking at. So there are two ways to represent an object in a free body diagram. You can mix it up, or you can do just pick one that you like and stick with that. So in order to represent the object in a free body diagram, we do one of two things. We can either represent the object with a dot or a square, okay? And these represent the object. Now, it doesn't matter what the object is. It could be a person, it could be a pair of scissors, it could be a ball, it could be a box. Whatever the object is, we represent it with either a dot or a square. You never draw the actual object in a free body diagram. The second part of the free body diagram is the arrows, which represent the forces acting on the object. Now there's two things to keep in mind about the arrows that you draw on a free body diagram. The first thing you want to consider is the direction of the arrow. Of course, the direction of the arrow should be going in the direction that the force is acting. The second thing you want to keep in mind is the length of the arrow. The length of the arrow represents the strength, or the magnitude, as we call it, of the force. Longer arrows mean larger or stronger forces. Shorter arrows mean weaker or lower magnitude forces. So now that we know what a free body diagram is and the parts that make one up, let's go ahead and look at an example of how to take an object out of reality and create a diagram that shows all of the forces acting on it. So here we see a man pushing a very large box across what we can assume is the floor. So remember, in our free body diagram, it's like we're taking this box and we are cutting it right out of reality. And when we create this free body diagram, we want to replace all of the forces that were acting on the object. So the first thing I'm going to do is draw an arrow to represent the box. Remember, we can draw that as either a square or as a dot. Since it's a box, I am going to go with the square option here. And I have my box represented. Now, the first thing that we want to do is analyze the situation that we have here and think about all of the forces that are acting on this box. So one great way to start any free body diagram is to start with that force that we know is always acting on any object in the universe. What force is that? Gravity. So we can almost always start right away by representing gravity. We know that gravity works towards the center of the Earth when we're on the planet Earth, which we know would be down towards the ground. So I'm going to go ahead and draw an arrow pointing downward from the box towards the center of the Earth, and I am going to label it weight, because we know that the force of gravity on an object is actually that object's weight, so we can just call that force weight. Now let's think about the other forces that are acting here. It's nice to sort of work in forces that are paired with one another. So we know that if gravity is pulling downward and this box is sitting on a surface, we also know that there's that other force that acts upward or opposite of the force of gravity. Upward from the surface, and that is my normal force. Now, two things I want to keep in mind here. First, I of course want to make sure that my arrow is pointing in the right direction. Another thing that I want to keep in mind is the length of my arrow. So the fact that this box is sitting nicely on the floor tells me that these forces must be equal or must be balanced. It's not being pushed up off the floor and it's not following through the floor. So that tells me that the normal force is exactly equal to the weight or the force of gravity. What other forces do we have acting here? Well, we know here that the man is pushing on the box, so we know that he is applying a force. He's pushing in the rightward direction, so in order to show that applied force, I need to show an arrow working in the rightward direction. I'm going to label that FA because I know that if he's just pushing on the box, that is an applied force. Now you might think, I think I'm done here. But you would be wrong because there is one other force that's acting here. So if the man is pushing the box this way along the floor, the surface of the floor, we know, will be applying a frictional force in the opposite direction. Now, to be super exact here, we would want to know if this box were actually moving, but we can go ahead and assume that it is moving in the rightward direction. So that tells me that the frictional force is somewhat less than the applied force that he is applying. Hence how he's able to push it in that direction. So I will draw my frictional force. I'll label it FF, and I will put it in the opposite direction of the applied force and of the motion of the box. Now we have a first complete free body diagram representing all of the forces acting on that box. Now let's look at this second example, which is similar to our first example, but slightly different. So let's think about what's happening here. If I were to take my box and cut this box out from reality with my magical scissors, what forces would I be removing from that box? Well, let's think about this in much the same way that we thought about the last one. So I will draw my square to represent my box, and I'm going to, as I usually do, start with the gravitational force or the weight of the box because I know it's always there. I also know that because the box is sitting on a surface, that surface, which is the floor in this case, is applying a normal force upward, perpendicular, you can see here, perpendicular to the surface, and that is going to be equal to the weight or that force of gravity pulling down. Now, what is different about this than our first example? Couple of things. Number one, instead of one applied force in one direction, we actually have two applied forces acting in opposite directions. So we can see here that our friend on this side is pushing with a 7 Newton force to the right, and our other friend here is pushing with a 10 Newton force to the left. So in order to show that, I'm going to draw my 7 Newton force here. And I'm going to actually label it because I know the magnitude of the force, I'm told right here, and a 10 Newton force going in this direction. Now you'll see that I know that the magnitude of this leftward facing force is greater than the magnitude of this force. Hence, I want to make sure that my arrow representing that force is longer than the arrow on this side, showing that magnitude. Now you may be wondering, well, what about friction? I'm going to tell us for this example to ignore friction because we don't necessarily know enough, but we can assume that if he's pushing with a 10 Newton force in this direction, the box will likely be moving in the leftward direction instead of the rightward direction. So friction would likely be moving in what direction? To the right. All right, another example here. We have our cow who is not wanting to go with the farmer here. So cow might thank us for cutting him out of this reality because he's not with it, but let's go ahead and do that. So again, I'm going to draw my square to represent my cow. Hopefully you're starting to get the picture that if I'm on a surface, I have my gravitational force or my weight going downwards to the center of the earth, and I have an equal but opposite normal force pointing upward or perpendicular to the surface. Now in this case, we see that my cow doesn't want to come with my farmer, but that farmer is still pulling. So we can see that there is a force acting about a 45-degree angle this way, So the question is, what is this force that this farmer is applying? Well, as you see here, this is a string or a rope. So if you remember, we would call that a tensile force or tension. So I'm going to simply label that FT. Now, if you wanted to get really complicated, which we won't, the cow is probably not moving in this situation, so you would think there is no friction. There is something that we call static friction. Even though the cow isn't moving, it's actually the friction between his hooves and the surface of the ground that's allowing him not to move. If there were no friction there, no matter what the farmer did, he could just pull that cow right along and it would go. So in this case, there is indeed a frictional force working opposite that tension, or keeping that cow from sliding along the surface. Final example here, we have a key that is hanging from a string. So we represent our key. We can always start with that force that's always acting, which we know is gravity or weight. Okay, now in this case, you may want to say, well, there is a normal force acting opposite to that weight. But you would be wrong, because this key is not sitting on a surface. So, since it's not on a surface and it's actually being hung by a string, it would still be an equal magnitude and opposite direction force going upwards, because we can see that the key is just hanging, it's not moving. But instead of a normal force, in this case, it is a tensile force or tension, because it is hanging from a string.